So we're in chapter 7, and we're talking about simple mixtures. Mixtures have a solvent and one or more solutes. And how do you tell the difference between the two, Alyssa? There's pretty much only one way between solutes and solvents. The solvent was always... How do you tell the difference between a solvent and a solute? There's always more solvent than solute. There you go. Yeah, so the solute's always the minority. And we're always going to be talking, in this chapter, pretty much binary mixtures. Shelby, what does binary mean? Binary means two. So there's only going to be two things in there. And we're not going to have any electrolytes, Jeffrey. That means there aren't going to be any what in the solution? Ions. No ions. No weak acids, no salts, no reactions. We're just doing simple mixing. Okay. So you take a look at these plots that they start out with. And they're mixing two things. Pretty much they're sticking with A's and B's here. All right? Or in this case, capital A, I guess. They're mixing capital A and two components. And the total volume seems to be changing, right? The total volume seems to be changing the more you're adding compound A. Or you look at this plot, and it looks like, look what's going on here. The volumes, one volume of solution's going down, the other volume is going up. They call these partial molar quantities, partial molar volumes. I mean, how could this even happen? If you take, I don't know, Kevin, you take 5 mils of water, or take 5 mils of one liquid, 5 mils of another liquid, dump it up, you should get 10 mils. That's not what this thing says. So you guys got to show this to me. So Alyssa, get 5 mils of water in here. Mel, this is ethanol, so you can get it in your eyes and everything. You'll just be a happier person.
I can drink it.
Yeah, it's pure. It's Everclear, so don't worry about it. Just get Jeffrey to open it. Okay, so get 5 mils in there and get 5 mils in this one. So once they get it done, we'll dump one into the other. We'll have Kelly dump one into the other. And we should get what volume?
10.
If we get 10, there's no point to this chapter.
We're not supposed to get 10. We want to get 10. We think.
Yeah, if you get 10, we can go on to chapter, what is it? Chapter 8. Exactly. Okay, so hand them over to Kelly. Oh, Kelly, first make sure there's 5 in each one. Make sure everyone believes. All right? No doubting Thomases here. Sounds a little over 5. Well, grab the little doohickey. Grab her doohickey. Jeez, Alyssa.
Follow me. Way back there or that much?
I didn't use yours.
Oh, who cares?
It's me? What do you mean who cares?
God, all I do is just tease people. I really don't care. Okay.
Drink it, see what if it's water.
Okay, so you got 5 in each?
Yeah.
Okay, and then dump one in the other one. Now, this part you got to be careful on. Make sure you get it all in there. Okay. Is it okay now? Is it well mixed though? Because we're talking about mixtures. So maybe Kevin, put your thumb on top of there and invert it a few times. What does the volume say right now though? What does the volume say right now? It's a little bit below 10. All right, let's mix them up a little bit better. So put your thumb on there really tight. Just give Shelby the ethanol bottle. And the pipette. And the doohickey. All right, that should be good enough. So what is the volume?
9.3.
It's not even close to 10, right? So this is a big deal. I mean, something that's as simple as mixing liquids and the volume changes, just think of the implications on this. Whether it's a manufacturing process or you're trying to get two machines to work and build these reactions or control these reactions or whatever the process is, mixing is all of a sudden turned into something pretty complicated. So, therefore, chapter 7. So we're taking a look at this first. Now they call them partial molar volumes. And all it really is V sub J. So J is the component, right? Water. So it'd be V sub water. And it's how does the volume change as you change the amount of water? And that's really all partial molar volume is it's the slope. And how is this volume changing as you change the amount of water in this mixture? You have to have a mixture in the first place, otherwise there is no partial molar volume. It is partial molar would be the total volume. So if you do have a mixture and it's just binary, here's your total volume, and it kind of makes sense. Here's the partial molar volume of A, the partial molar volume of B, and if it's partial molar volume, would probably be the units on it, Shelby, or VA or VB. They probably have units of, yeah, you could have meters cubed or liters all over moles. So it makes sense that if you multiply the partial molar volume by N, which would probably be what, Kelly? The moles. Little NB would be the moles of B, right? If you multiply by the number of moles, you get volume units. So then you get the total volume. Okay. The partial molar Gibbs energy. Okay. So how does the Gibbs energy change as you change the number of moles? So this is kind of the hidden underworkings with chemical potentials and things. And total Gibbs energy of a mixture. I don't think you're going to use these equations too much. But I thought this one was kind of interesting. The Gibbs-Duhem equation. And what it's for, leave it down here, are these partial molar quantities. That's what that xj is. These partial molar quantities, like Vm. So, for example, what we're messing with, it has to equal 0. So we have two components in our mixture, A and B. So if I put that in my sum, I should have two terms, an A term and a B term. So I have N is the number of moles, right? And little differential molar volume of A, and number of moles of B. All right, so how does these? So what's changing here is this little differential, the molar volume, and all they're trying to say is, if this one increases, let's say the molar volume increases in this composition range. If that one goes up, well then this one has to go down because the sum is 0. And that's exactly what's happening up here, right? As one partial molar quantity it's increasing, the other one's decreasing in a mixture. So this only works in a mixture. It's not a property of the substance on its own, right? Because you have A and B in here. These are mixtures. This whole chapter is about mixtures. And we talked about the assumptions already, right? No electrolytes, that kind of thing. Thermodynamics of mixing two perfect gases. Do gases mix, Mel? Is that a spontaneous thing? Gases mixing? Is that something that happens spontaneously?
Yes.
Yeah, good luck good luck trying to stop it, right? So it's a very spontaneous thing. That delta mix G needs to be a what number then? Needs to be negative. If you look at that equation, is it negative? What are the x's? Mole fractions, right? And Alyssa, how are mole fractions defined again? Like if I pick one, if I pick XA, how is mole fraction? Well, let's pick the one inside the natural log. How is it defined again?
Isn't that wouldn't be
Well,
it's like in a concept review, right?
yeah. So the mole fraction of A is equal to what over what? Moles of? No, you're thinking too hard.
Moles of one.
Moles of 1 divided by the
Sum of the two.
the total moles. So the mole fraction of A would just be the moles of A divided by the total moles. So that would be like, I guess if you want to use the symbols, right? That's what mole fraction of A would be. Our mole fractions are always what numbers? They're always smaller than, they have to be smaller than 1. There you go, Shelby. The ln of numbers less than 1 are always negative. So no matter what, you're always going to get a negative number for delta G. So if you look at the same story for entropy, for mixing, that should always be what? Positive. Is it always positive? And why is it always positive? Yeah, there you see it. Right there. Because you got that negative times a negative. Exactly. And this one I didn't even write anything on. Because it's 0. Because we're talking about perfect gases. So there's no heat involved. There's no interaction between these gases for a perfect gas. And then we are getting into ideal solutions. Raoult. I should have named my kid Raoult. I like Raoult. Raoult.
Raoult?
Yeah, doesn't it sound like a cool name? That and Celsius.
I named my dog Celsius. Celsius.
So Raoult is for the solvent. What does that mean? So you have a mixture, and you have a solute and a solvent, and Raoult's law helps you describe the solvent. PJ is what, though? Density would be this symbol. Pressure. Okay, now what kind of pressure? The vapor pressure. Because you have to imagine this kind of thing. And it's a solution, and what they're interested in is the vapor pressure of the solvent. And why is vapor pressure such a big deal again? Because it rules when what happens? Or it has a real integral component in it. Boiling, right? Right? Why? The idea here, they're trying to illustrate it here. Whether this is actually happening or not, I guess. I don't know. I guess these guys know more than I do. So looking at this diagram, right? What would you identify, Kelly, as the solvent? Do you see more than one type of molecule there? The green ones. Green ones would be the solvent. A little dinky, I don't know why they made them so tiny, right? Solute doesn't have to be small, but anyway, they made them really tiny. So the little guys are the solute. And what they're trying to say is that what's going to happen to the vapor pressure if you add a solute, Jeff, to a solvent? Can you get that out of that diagram?
Adding a solute to a solvent.
Yeah. I don't know if you can read that little dinky word there. Right? It blocked. So they're trying to say that the solvent has a harder time getting into the vapor phase. So if the solvent has a harder time getting to the vapor phase, its vapor pressure goes down, right? Well, if its vapor pressure goes down, Melissa, what happens to the boiling point? The vapor pressure of the solution magically goes down. Did the boiling point change? At all, even? Right? Because now it's not the same solution anymore. Because let's say it was water. Fine, it was water. Should boil at 100 degrees Celsius at, on the phase diagram, one atmosphere pressure. Add something to it. Add a solute. Vapor, now you have a different solution. Vapor pressure just went down. When do things boil again? When what equals what?
External equals vapor pressure.
When external equals vapor pressure. And what's the only way to raise the vapor pressure of this thing? Turn on the burner, increase the temperature, heat it up, right? So now, do you have to heat it up to an even higher temperature if you dump some solute in there? Yeah, because now you're starting even at a lower vapor pressure. You have to kick that vapor pressure up to reach the external. The external pressure didn't change, but your vapor pressure just did. It dropped like a rock. So you add a solute to a solvent, man, now you just screwed up the vapor pressure. You screw up the vapor pressure, you decreased it, and then that means you screw up the boiling point, because now it's going to have a higher boiling point. You got to heat it up even hotter. Okay. So is that the solution to what? If you remember this, you're doing pretty good. And if you had me for general chemistry, give you a hint: Colorado, macaroni and cheese. Yeah, so those guys in Colorado, they want to make their mac and cheese. They got to cook it longer than Jeff does here in San Antonio. Why?
They can't get the water hot.
They can't get the water as hot. Why?
Because the boiling point's low.
The boiling point's lower. Why?
Because the pressure is lower.
The pressure is lower, not higher. Right? The pressure's lower up there. So the external pressure's lower. Vapor pressure reaches external pressure a lot easier up there. Right? So they can't get it as hot. So what do they do? Or what does the manufacturer do? He alters the directions for high altitudes. And it says do this, this, this. Right? Now people are touchy on their salt, so they could have just dumped in some salt, right, and done the same thing. But okay. That's the thinking there. So you have a so if PJ is a vapor pressure of the, and J is just whatever, if water's your solvent, then J would be water, right? XJ would be what? Mole fraction of the solvent. PJ star. PJ star. What was PJ again? Not partial pressure. Vapor pressure, right? Well, I guess it's technical speaking. If you have a closed system, the vapor pressure is the partial pressure. You're right. But I think it's safer just to call it vapor pressure because it's more visual. At least it is for me. PJ star. And it'll help you answer what PJ star is, too.
Vapor pressure emission?
Kind of. The star just means pure. So remember you have this mixture idea going. And the vapor pressure keeps dropping the more solute you add. So if you don't add any solute at all, that's the vapor pressure of pure. Yeah, so this is the vapor pressure in the tables, right, for pure components. So that number you can get from a table. This is the vapor pressure of the pure solvent, right, the pure solvent vapor pressure. So the more, see how the mole fraction changes, it has a huge effect on the vapor pressure. Henry's law has to do not with the solvent, but the solute. Okay. And this K is called the ebullioscopic constant. And this is all for the solute, right? So Pj, how would you define it, Kelly? If this whole equation's for the solute, Pj would be, you said, yeah, but vapor pressure of what? We're talking about Henry's law now. Pj is what? What of the solute? The vapor pressure of the solute, exactly. That'd be vapor pressure of the solute. So if we stick to, I don't know, the book seems to do this. They're sticking pretty good to A being solvent and B being solute. So if that's the case, you could pretty much rewrite this expression as PB equals XB KB. The book seems to be pretty good about that. But it doesn't have to be that way. Just so if PB is the vapor pressure of the solute, XB is the mole fraction of the solute, KB is the bilioscopic constant. So what could you plot? What versus what to get KB? You could plot what on the y-axis, what on the x-axis to get KB.
Mole fraction on the x.
Plot mole fraction on the x, and then what on the y? Okay, then how are you going to get KB out of that? It's the slope. The y-intercept theoretically should be what? 0. Yeah. I think that's a homework question. Does the solute have to be a solid? Alyssa, does the solute have to be a solid? Are all solutes solids? No. Solutes. Remember, just what's the rule between identifying solutes and solvents? More solvent. Yeah, that's the only thing you got to remember. That's about it. So let's jump into this stuff. The partial molar volumes of acetone and chloroform. I better start writing this stuff down. That's mole fraction of acetone and chloroform. Mole fraction is this. What is the volume of a solution of a mass 1 kilogram? Okay. So they want to know volume. Out of all this stuff, Kevin, that we've looked at, where would you start? They're after volume.
So the total volume of the two components?
Yeah, I would start here too, because it's got the symbol of our answer. It's going to guide you where to go. I would start there. You might as well put in chloroform and acetone, right? So we're trying to find this one. Which ones, do we know any of them, Kelly? Do we know any of the other variables? Yeah, we know the molar volumes of acetone, and we've got that one. We've got that one. So what do you think? Anybody have an idea to get the... We gotta find these. We need these. Yeah, how are you gonna use mole fraction in this mess? Or do you even need it?
Because you can just take the grams times the molecular weight to get the moles.
Yeah. We could take grams times molecular weight to get the moles. But you know the grams of each.
Oh no, just total.
Oh, just total.
Right?
Yeah, it's just total. But that total mass would be grams of chloroform and grams of acetone. Which you're right, that's equal to the number of moles of chloroform times the molecular weight. How do you... This number has to be good for something. This 0.4693, that's the mole fraction of this chloroform. And that's really equal to what over what? The moles of chloroform all over moles of chloroform plus the moles of acetone. Right? So you have what we can do here. What's the trick to doing this? I forget what I did. Moles of chloroform.
Is 1 minus that going to give us the other mole fraction?
Yeah, the 1 minus that would give us the other mole fraction. What did I do? I forgot. How did I do this? Oh, stupid. Okay. So how do you get the moles of 1, right? If you know the, let's back up. We hardly ever use mole fraction, so it's so hard to remember to do all this stuff. Okay, if you know the mole fraction of A, right? That's the moles of A all over the total moles, right? So if you multiply this by the total moles, right, you get the moles of A, right? So pretty much that's what we're going to do. We know the mole fraction of each one. We know the mole fraction of chloroform and acetone, right? But how did I get the total moles? What did I do?
I thought you only know the total moles of chloroform. I mean, the mole fraction of
it's the 2 steps. That's why. You can't solve this all in 1 step. Okay. I see what I did. So that, we were on the right track. We were on the right track, though. So that 1,000 grams, right? That's everything. And like we said, that was the grams of acetone, grams of chloroform. And then, like we said, that's the moles. We were on the right track. Molecular weight of acetone. And then the mole fraction. Man, I think I'm getting dehydrated. What the hell did I do? 1,000. So I solve for n total. I solve for n total. Because then this would be the mole fraction of acetone times n total times the molecular weight of acetone. All right, you see how this part is that, right? 1,000 grams has to equal this. And then my mole fraction of my chloroform times n total. See what I did? This is equal to this, right? You take mole fraction times the total, and then you get, right, the moles of it. That makes sense? That's what I did for both of these. Then you solve for n total. And once you get n total, you go back and you say, okay, well, I know what the mole fraction is. So take it times n total, and I'll get the number of moles of acetone. And then you convert it to grams, because you know what the molar mass is. Oh, man. So it's confusing because it's really 2 steps. First, find the total moles. That's how I did it. First, find NT. And then once you find NT, then find the grams. Then find the number of grams of each. Oh, maybe there's an easier way to do that.
Wouldn't we treat the mole fraction as a fraction? We try to solve for algebraically what it is.
Yeah, wouldn't that be easier?
Right, because it'd be 4,693 divided by 10,000. That's the mole fraction. So then you just simplify it.
But I think the problem, though, is that mole fraction is a weighted sum. So you can't take 0.4693 times 1,000 and say that fraction is your mass. No, that it's mole fraction, not weight percent fraction.
Oh, I think I get what
So
you're saying.
I don't think you can take the 0.4693 and take that 50% of mass of 1 kilogram to be the mass of chloroform. I don't think that's going to work because it's a weighted sum it's weighted by molecular weight.
That's assuming, you're assuming there's a total of 1,000 grams.
So if they gave us the total number of moles, then it would work. They said the total number of moles was this, then we could say percents. So I think this is the type of thinking that's going to get you through a lot of these. The density of a 50% biomass ethanol water solution is 0.914. So calculate the partial molar volume. They want the partial molar volume of ethanol. It should be this type of thing again, right? The total volume, number of moles of ethanol, partial molar volume of ethanol, water, partial molar volume of water. And they told us this one. They told us the water. That one we know. It's 50% by mass. What does this mean to you? 50% by mass.
So their amounts are equal to each other.
Yeah, in what amounts? Not in volume, in weight, in mass, in grams. So if we said the easiest way to do this would be to say the total volume is what? Then you know the mass. Total volume is what? This is gram. This should be a per here, right? Because it's density. See, the volume is. What unit is this? Cubic centimeters, right? Same as a milliliter. Say that this is 1 cubic centimeter. That's your total volume. Then your total mass would be.
So each of them, what is saying?
Your total mass would be how many grams?
0.5.
If I have 0.914 grams per cubic centimeter, I take 1 cubic centimeter of this solution. How much mass do I have? 0.914. And it's 50% by mass, so what mass of it has to be ethanol? What mass of it has to be water? Yeah, so divide 0.914 by 2, and you'd have the mass of each. So that's if you take 1 cubic centimeter. So just convert, what's 0.914 over 2? 0.457? So convert 0.457 grams of each into moles, and then you'll have those parts. And then solve for this guy. This is what they want. Here's the density, here's the plot one. This is the plot idea that we talked about. And then do you recognize these? Raoult and predict the partial vapor pressure of HCl above its solution. So they want Raoult or they want Henry's law. In liquid germanium tetrachloride. Yeah, I think it's Henry's because HCl is the solute. So you got to use Henry's. So use Henry's, no big deal. And then, all right, we're kind of out of time, but you can figure out 6, I think. So have a good weekend.